Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on metal fuel for prototype generation 4 SFR design, fabrication, and qualification will be presented by Dr. Chanbok Lee. At this time, it's my pleasure to introduce Dr. Patricia Pavier. Patricia is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's also the chair of the Gen 4 International Forum Education and Training Working Group. Patricia.
Thank you so much, Bertha, for the introduction. Good morning, good evening, everyone. Pleasure to have Dr. Chanbok Lee with us today. He has been working at the Korea Atomic Energy Research Institute since 1989. He worked on the design, fabrication, and post-irradiation examination of uranium dioxide fuel for the commercial PWRs in Korea. After that, he worked on the development of diverse fuel for PWR, research reactor, and very high temperature gas cool reactor. Since 2007, he has worked on metal fuel development for sodium fast reactor. He received his bachelor and master in nuclear engineering from Seoul National University in South Korea, and his PhD in nuclear engineering from MIT in the United States. He served as division director of fuel development at Carry, chair of nuclear fuel and materials division in Korea Nuclear Society, and co-chair of OECD NEA Nuclear Innovation 2050 Fuel and Fuel Cycle Subgroup. So without any delay, I'm going to give the floor to Dr. Lee. Thank you again, Dr. Lee, for volunteering to give this webinar. But before I do that, again, for the people who want to have access to the slides, you have a box. It's called Hands Out. And in this box, you will find the webinar and the flyer. So Dr. Lee, you have the floor now. Thank you again.
Thank you very much, Dr. Patricia Pavier, for kind introduction and giving me opportunity to present at this webinar. And I also would like to thank Ms. Bertha for organizing this webinar. Hello. It is my great pleasure to introduce our work on the metal fuel development for PGSFR in this webinar. This work is actually the result of the many people, over 100 people in our institute carry for almost 15 years. So today my presentation will cover the first introductions. I will briefly explain the background of this project. Then I'll explain our pure development work from pure design, pure fabrication, and pure qualification for licensing application. Then finally, I'll summarize and explain our future plan. In Korea, also in our institute carry, we have been developing the pyro-electrochemical pure recycling in SFR. So from the spent fuel or light water reactor fuel, we pyro-electrochemical processing will recover uranium and the TLU element together to fabricate the fuel for SFR. And in this SFR, the transmutation of minor actinides can reduce the environmental burden and repository space, and also can enhance the utilization of uranium resource. So For the fuels, we selected the metallic form of the fuels for this SFR. As you know, the metallic fuel has a higher thermal conductivity, so it can keep the fuel temperature low. So based on that low temperature, the inherent passive reactor safety can be achieved due to these characteristics. Also, the metallic fuel can accommodate more minor actinides, so it can transmute more efficiently the minor actinide. And by recovering the TRU, plutonium and minor actinide together through this pyro-processing, so there is more proliferation resistance. So by these characteristics, we can meet the target of generation 4. For example, sustainability, safety, economy, and proliferation resistance. So I have to mention this metallic fuel in SFR is based on the much experience accumulated in the United States. As you know very well, the EBR2 and experience irradiations and design work of the IFR and PRISM. So during this work, we have a very good collaboration with the research organization in United States, like Idaho National Laboratory and Oregon National Laboratory. And this table shows the design characteristics of the PGSFR. I said its general purpose is the demonstration of the TRU transmutations coupled with pyro processing. So initial fuel, driving fuel is the uranium zirconium fuel, which was the much verified in the United States. And later we will qualify the TRU fuel in this reactor, and TRU fuel will be the main fuels in later stage. The electric capacity is about 150 megawatt electrics, and the core outlet temperature is 545 centigrade. And for safety, because of the metallic fuels, high thermal conductivity and low temperature, the core damage frequency of the 10 to the minus 6 can be easily achieved. And also the at the bottom, for hypothetical accident of the station blackout, the reactor can be maintained safe more than 3 days. Depending on design, it can go much longer than this time. This shows the core design of the reactors. Its thermal power is about 392, and the inner temperature is about 390 also. And the fuel used the LE fuels about 19.2. It can reach the cycle length about 290. And the cladding is the ferritic magnetic steel, which has a very low swelling rate. And the core height is about 90 centimeters, and the pure diameter is about 7.4 millimeters. And the average burn-up is about 66 kilowatt per metric tons. And this shows the pure characteristics. pure designs. So for this pure design, we collaborated with our national lab. They have very much experience. So here, pure slug length is about 90 centimeter, and there are bigger ranks of the gas plenum because about over 80% of the fission gas generated in the pure are released to the plenum. So there lead large volume of the plenum length. And here you can see the pure assembly. The length is about 4.55 meters. Even though the pure raw length is about half of the size. And between bottom and the top of the pure rod, there is a reflector. This reflector protects lower and upper structure of the core from the fast neutron coming from the pures. And here is the handling socket and the nose piece. So the sodium coolant is going here and flow. And for this reflect design, we adopt a block type reflect. It's simple to fabricate and maybe possibly it can be reused after discharge to other fuels. So the main reason to this one is the easy to fabricate. That is the main reason to change to adopt this block type reflector. So I explained our pure design. As you know, in pure design, there are some parameters to be considered with discharge burn-ups, peak pure power and peak pure temperature, and peak cladding past neutron influence. These are related about pure burn-up. So it's better to achieve the higher burn-up and the higher temperature to get pure economy. So taking into account those parameters, pure design basis set. Basic requirement is to maintain the pure integrity during the operations. For pure temperature, the pure melting need to be prevented, and eutectic melting need to be controlled during the operation. For cladding, there are some cladding behaviors during the irradiations, like creep, swelling, and the cumulative damage correction and strain. Those criteria need to be checked and verified to verify the pure integrity. So considering all those parameters, we finally set pure design. It include pure dimensions, pure shapes, and arrangement, and the compilation of the pure assembly. Also, the selection of the right materials of pure component need to be done. Excuse me. So this shows the typical irradiation performance of metallic pures. And in the pure, there are fission is occurring. So fission gas generated are released to the our pure slug. And as you can see here, as a burn-up, after burn-up about 6, almost 70 or more fission gas release. Fission gas are released to the gas plenum, and the pure metal pure swelling and actual growth occurs. This shows the microstructure of the pures. There are bubbles filled with fission gas, and some fission gas are released to the outside of this pure slug through these open channels. Here you can see this is before the irradiation. There are lots of the void sodium space, and after irradiation is all it's swelled and it contact with the claddings. And also during the irradiations, pure element migrate by diffusions. Because of this behavior, this pure element can migrate inside or outside, depending on the each element's thermodynamics. For cladding, on the cladding, there is always the tensile stress. So because of that, the cladding is clipped out, and also the high fast neutron flux, the irradiation swelling occurs on the cladding, and because of these two behavior, cladding ductility is also reduced. This shows the cladding swelling. This is the H9 data. H9 has the body-centered cubic lattice structure, so it shows the lower swelling rate. And this one is the oscillator claddings of a page-centered cubic. It's more closely packed, and it has a higher swelling rate. Also, the pure and the cladding are both metals. There are some they can occur some chemical pure cladding chemical interaction like that melting or cladding wastage. Also, so because of some tensile stress, and also the pure swelling, there are some pure cladding mechanical interactions can occur. This shows the design analysis result of our pure design in this PGSFR, as I explained that. And pure design correct for pure rod, the design criteria for normal operation and operational transient, pure integrity should be maintained. So we need to check the pure temperature, cladding strain, and cladding CDF, and also cladding pure cladding chemical interaction. So considering all the uncertainties like reactor operation uncertainties, also pure fabrication tolerance, we analyze the pure behavior conservatively, and even though with those conservatism, the maximum pure temperature is about maximum cladding middle temperature is about 652, and the cladding strain is 0.54. The criteria is 1%, and CDF is the 0.05, and it is satisfied. And also the maximum pure central temperature is about 715. It's much lower than the melting temperature. So we confirm the pure rod integrity is maintained. Also for pure assembly design criteria is more than the pure rod. The pure the integrity of the pure assembly needs to be maintained. The normal operation also for design-based accident. because to have to keep the pure core structure shape, pure assembly need to be intact, even though even under the design base extent. And this show the pure fabrications. This one is the pure slug, and this one is the pure cladding, and pure rod, and pure rod wire, and reflector, top and bottom, and nose piece, and handling socket. And this is a hexagonal pure assembly duct. And this shows the full size pure assembly fabricate. And inside the pure assembly, you can see the array of the pure rod here. So I explained how we fabricated all those pure components. First, pure slug casting. Initially, we made a lab scale about patch size is about 2.5, and we tested different composition of the pure slug to find the optimum condition of the pure casting, like temperature, pressure, heating rate, and duration times. Then we make engineering scale about 20 kilogram per batch here, and made a pure slug, and check the pure slug to meet whether to meet the pure specification like dimensions and zirconium content homogeneity in the pure, and the impurity level in the pure slug is all was checked to meet the pure specifications. And next, this shows the general steps for pure cladding tube. Here, from the ingot melting, forging, and machining, hot extrusion, drawing, and pilgering, and the heat treatment, and final cladding tubes. So to fabricate the cladding tube, we collaborated with the steel company in Korea to fabricate the cladding tube. So from about 1 ton size of the ingot, meltings, forgings, and through these steps, hot extrusions, drawings, and pilgering. After pilgering, we fabricate the cladding tubes. And the final size about 3 meters of these dimensions. So we fabricated this cladding, first H9 cladding tube, and also we fabricated some advanced cladding. We call it FC92. So we fabricated 2 separate cladding tubes in cooperation with this company. So H9 is very good cladding, and the irradiation database is a lot. And so to achieve more higher burner, or to reach the higher core outlet temperature, we try to develop the high advanced claddings which have a better performance, especially in high temperature. So we tested about 38 alloys, and by changing the alloy composition and heat treatment, we developed one alloy we call the FC92, and we fabricate, and by the test it showed about at this high temperature 650s it has cleavage strength was improved more than 30%. So we fabricated the cladding tube of this FC92 also. This showed our work on the pure rod fabrications. Inside the pure rod, there is a sodium bonding. Sodium is very good thermal conductivity. So to lower the pure slug temperature, there is the sodium bonding between pure and cladding. So from the claddings and the solid sodium is loaded into the cladding at room temperature. Then the pure slug inserted at top of the sodium, and the end cap is welding, and sodium bonding is done. So through the diesel at this time by the through the X-ray examinations, we can check how the sodium bonding is good or there are some pore, or so we can check, and it works well. And through this process, we fabricated 12 pure rodlet to irradiate in our Hanaru research reactors. This one showed pure rod wire and pure assembly duct. It's made from the H9 for wire about 1 tons ingots through the rolling and drawing. This wire was fabricated. And for the duct, it's tough work to fabricate a long hexagonal duct. So from the 3 tons of ingots through this process, forging, piercing, drawing, and heat treatment, we finally succeeded to fabricate this duct, the length of the permit, thickness of 3 millimeter to meet the specification, especially the uniform thickness and straightness of this duct. And as I said before, because the metal pure and metal cladding, there can chemical interaction can occur. So we developed, we investigate the barriers to prevent this chemical reaction. The barrier function as a diffusion barrier of the element. So we tried the diverse barrier candidate, and good behavior was found for this barrier: chrome, vanadium, and chrome oxide. And these are the chrome can be electroplated on the inside surface of the cladding, and the chrome oxide can form by oxidations of inside the cladding, and other electrification and liner also we did studies. And also we studied not on the cladding inner surface, also the surface oxidation of the pure slug itself. It's easy to make form because it's uranium pure slug surface is easy to oxidize, so we can form the very thin thickness of the oxide here. And we tested the chemical interaction between cladding and pure slug, and it works well. So based on these results and for practical reasons, we chose the electroplating of the chromium is the main behavior candidate. So this chrome electroplating, this is the apparatus for electroplating of chromium on the inner surface of claddings. And by about 20 micrometer thickness of the layer was placed on the inner surface, and we did ROPI test and also then make a cladding and make a pure rod, and we did irradiation test in Hanaro here, and I'll show later it works well to prevent interdiffusion between pure and claddings. So this showed the result of our irradiation test in Hanaro. Including the current pair. We did fabricate 12 rodlet for difference and pure composition and with chrome barrier and this size. First one is achieved about 3% of burn-up for this 182 days, and the PI was done. And after that, we fabricated 12 pure rodlets of similar. First one is we are very careful. So this one was irradiated low burnup, also at low temperatures. It's about maximum cladding temperature is about 550, and so it's good. The pure was there was no pure failure in this first one. So second one we fabricated, and this one was designed to reach about higher temperature of the cladding, inner cladding temperature, and to achieve higher burnup. But even though we complete the fabrication, we are still waiting to be irradiated because of some operation problem in the Hanaro reactors. This shows the PI result of the Hanaro, and before the irradiation and after irradiation, about 3% burnup. And this red point showed the fission gas release state. It's low burnup, so there are some scattering. This measure data, and there was some. This showed chromium barriers, and it works well. The barrier was intact, and the thickness was there, uniforms, and there found some crack here for cladding. So we worked later. We worked to prevent this cracking. We worked on the improve the electroplating process of the chromium to prevent by forming the smaller grain size of the chrome multi-grain on the chromium filaments. And also we did irradiation test in the FAST research reactor POR60 in Russia. So for that we fabricated also about 12 pure rods fabricated in our institute, and then we transport this pure rod to the POR60 for irradiation test. And during the irradiation, the peak linear power is changing about distance 364 to 319. depending on the reactor operation conditions, also depending on the pure rod positions. And peak cladding temperature is about 650 to 617 centigrade. So during this 11 test reached in May 2020 is about 7.20%, and there are some interim non-destructive examination of this rod. This showed that non-destructive examinations like appearance, gamma scanning, and cladding probability to measure the cladding diameters. And we have planned to extend this irradiation up to the 10. So we are waiting our government approval for this extension. As separate, we did also test the cladding samples in this BR60 to check the cladding properties. So we used the two material test rigs, both the FC92 and H9. So we tested these two cladding materials at the same condition to compare the behavior of these claddings. And two material tests of different temperature and different irradiations. So the irradiation total achieved up to the August 2020 is about this one, 46 and 77.5 dPm. And the interim inspection was done to measure the cladding diameters and cladding density to derive the cladding creep and the cladding swelling. So this is show the picture of the interim expansion, and those are the test rig and irradiation specimen for the creep and swelling, and microstructure also, as also the for tensile test purpose. And for those claddings, FC92 and H9. H9 is has about 12 chromium content, and FC92 has 9 chromium contents. So to check whether there are any difference in the chemical interaction behavior, we did some comparison test with the pures, and it found there was no specific difference between this cladding. And also by using the irradiated pure, irradiated in Hanaro, about 3% burners, we did annealing test in the hot cells to check the FCCI behavior. And this show that this is the annealing test equipment in the hot cell, inside hot cell. And this showed the FCI test result of this 11 pures, and it found about 800. Therefore, some eutectic reaction was found. So through this test, we make some data base to confirm our pure behavior and to be used for our licensing purpose later. And for the verification test of our full-size pure assembly, we for hydraulic test of this pure assembly, we construct a test facility for for hydraulic test of the pure assembly. This is operation condition. This is the have a similar Reynolds number of sodium. So this assembly is for the used in the sodium cooled reactor. So at the similar condition of the using the water, we did test here to, for example, pressure test of pure assembly and hydraulic lift up and hold down test by changing the flow rate of the water, and also check the flow induced vibration test using these facilities. And this is for the mechanical test of pure assembly. We used the existing facility, which was the used for the light water reactor pure assembly mechanical test. So we made some slight change to accommodate our SFR pure assembly here by installing some sensors. We did measure the pure assembly structural response, like vibrations characteristics, lateral bendings, and actual impact. So through these tests, the pure assembly structural integrity was verified in these tests. And also stress and strain was measured on the maximum withdrawal force to simulate condition in SFR, in-batch transport machines. Excuse me. So so far I explained our work on the uranium fuels, the fabrication and verification for licensing of our this fuel for our PGSFR. Next, I explained our research on the TRU fuels, which we used late stage of the this PGSFR. Anyhow, we need to show the technical feasibility of this TRU fuel recycling. So we did work on this TRU fuels. So as I said before, through the pyro-electrochemical processing of the spent light water reactor fuels, TRU extracted and pure fabricated, and then it will be inserted in the SFR. So pure design itself is same, only the pure composition of the pure slug are different from uranium-10 zirconium to uranium-TRU zirconium pures. This is the in this TRU ingot, there are some impurities of layers about this four layers element of its typical composition ratio, and this layers has similar electrochemical characteristics to the mining actinide. So they comes together with the mining actinide. So we need to take care of the these layers during the fabrications and also irradiation behaviors. Excuse me. Yeah. You may know where this TLU fuel has there are radioactive, highly radioactive elements like curiums, americiums. Because of that, this fuel should be handled in the shielded environment, like hot cells. So fuel needs to be fabricated in the hot cell remotely. So that is the challenge for the fuel calculations. Also, the americium is volatile. So during the melting of the pure ingot at high temperature, americium can be evaporated. So those evaporation need to be controlled. And also the rarest element, impurities, they are very chemical active. So those need to be taken care of for pure fabrication. So there are for pure fabrication, those are the challenging, and also the irradiation performance of these TLU fuels with some rare impurities and also minor actinide. Those need to be checked, and because of the this layers of the barrier technology is more helpful here for TLU fuels to prevent. So those are about the irradiation performance side of the TLU fuel. And because of that, high advanced cladding to achieve higher burn and higher temperature is desirable to enhance the economy. So those are the three technical challenge for the TLU fuels. So we worked on this one. This shows the typical composition of the feeder spent fuels. About 1 tons, almost 2 fuel assembly after cooling 40 years. There are mainly the uranium left, and there are some plutoniums, this amount, and minor actinide, and fission product. In this fission product, there are some lanthanide. Layers is included in this lanthanide element. And from these spent fuels, pyroprocessing extract TLU element through the 2 steps. First step is to convert this uranium oxide to the metal reductions process. And second stage is from the metal to TLU is extracted through the electrochemical process. For the remote fabrication technology studies, we installed the mock-up remote facilities here, and we, through the many development work, we finally make engineering scale of the pure slug casting. And with that casting apparatus, we use the copper, make a slug, and copper and nickel, and finally we make uranium zirconium through using these mock-up facilities like remote operations. Still, there are a long way to go, but we just show that it can be fabricated remotely. We need to work more to fabricate this pure slug, more automatic operations and more reliable operations. And we did study also some innovative design of the fuel, especially for the TLU fuels applications. This one showed the particulate fuels. So by this atomization process, this is the melt ingot and this high-speed rotating plate. Then the spherical particle can be fabricated by this atomization equipment. This is well established in our institute Cary. This technique is used to fabricate research reactor fuels in our Hanaro reactor. So by using this equipment, we fabricated particulate fuels of uran-10 zirconiums. We can make a different size by changing the rotating conditions. And we fabricate particle and we consolidate by the sintering process like this size. Then this fuel can be inserted in the claddings. So advantage of this particular fuel is because the pure particle can direct contact with the cladding from the start. So sodium bond can be removed on this design. And also by using this process compared with casting. In the casting, we need a mold and we need a crucible. So those mold and crucible is not needed here. So the waste generation, especially for TLU, pure casting, waste generation can be reduced. So that is the advantage of this particular fuels. So we can fabricate this one, but it's still unknown how it will behave during the irradiation. So the irradiation test need to be done to verify the irradiation behavior of this particular PEP, how it will behave during the irradiations. We need to do that, this test. Also, we are working on the annular fuel slug. Annular has also advantage. We can also remove the sodium by making this annular fuel slug direct contact with cladding. So by using the copper, by extrusions, we made this annular fuels, and this one is the extrusion of copper, and we cut it to check the microstructures. This is the copper is the current stage of this work. And for barrier, for more stronger barrier, we worked on the liner cladding. So not electroplating of the chromium. This one is another thin tubes of the barrier, like the liner candid zirconium or titaniums about this thickness, 50 micron thickness liner was fabricated by the co-drawing and filtering steps. And we fabricated the liner cladding about the length of the 1 meter with the two different liner. So we are working on for this process also. So those are the work for the TRU fuel behavior and fabrications. So in summary, I explained so for initial fuels, so uranium-10 zirconium fuels, we fabricated the fuels in collaboration with the Korean steel company, and by fabricating the full-size fuel assembly, and we did test of hydraulic and mechanical test for the licensing of the this drive fuels. Also, we have been working on the TRU fuels recycling to show the technical feasibility of the TRU fuels from the pyro-electrochemical processing of the light water spent fuels. Today, I didn't cover our collaboration work with Idaho National Laboratory. We call it Joint Fuel Cycle Study. We have been worked together for last 10 years for pyros processing, also the TRU fuel. So from the spent oxide fuels, TRU element are extracted by the pyro processing, and this TRU material was used to fabricate the fuel in hot cell, and it was irradiated in the ATR in Idaho National Laboratory. And the irradiation was done so far about 5.5% burnup, and with some PIE, and there was no specific, no anomaly. So it's behaved as expected. So it showed good behavior. So it showed some feasibility. We can say that this recycling of TRU in through the pyro process. So we hope to continue this work after approval from the government. So and now in Korea, we finished those work, and we generated data for licensing for the PGSFR with the uranium-10 zirconium. We did finish the basic design, and so we can at the state to start preliminary safety analysis if the government decided to construct reactors. So, but we are still waiting this year the final decision of the Korea government. But I personally think there was some positive signal because of the our research result to show some promising result. So even though the schedule may be the construction of the facilities and reactor may be proceed in long-term schedule, but I personally expect it continues also. And also, as you know, this net zero from in the world to reduce the carbon dioxide released into the atmosphere. There is some new more interest in nuclear power plant constructions. Then in later stage, like 2040 or 2050, this past reactor have more again have more interest. And also, as you know, well, in the United States, and there are some good projects going on, like natrium reactors and also VTR construction. Those are all based on the metallic fuels and SFRs. So I hope these projects are going well, and it will also help our project also in Korea. Thank you very much for a long time. It's all my presentation. Thank you.
Thank you, Dr. Lee. If we have questions, please go ahead and type those into the questions pane. While questions are coming in, we'll take a quick look at the upcoming webinar presentations that we have planned. In November, geometry, design, and transition simulation of a heat pipe microreactor. In December, development of an austenitic martensitic gradient steel by additive manufacturing. And in January, ESFR SMART, a European sodium fast reactor concept, including the European feedback experience and the new safety commitments following Fukushima accident. We have questions. Bear with me just 1 minute, please. So Dr. Lee, there's a question. Dr. Lee, has there been any consideration for using a fuel without sodium bonding in case the pyro process is unavailable and the fuel needs direct disposal?
PLA fuel without sodium bonding?
Correct. Considering using a fuel without sodium bonding in case the pyro process is unavailable and the fuel needs direct disposal.
It's possible, but it's a long way to go. So it may be possible, but I can say it's not our prime candidate for our fuels. So for example, the particulate fuel design is work well, then later this sodium bonding can be omitted in these fuel designs. So it has some possibility to remove the sodium bonding, but it's in the late stage, I can say. Yeah.
Thank you. Was the swelling of this metal directionally dependent on any way, or did it uniformly swell from irradiation?
Yeah, it's quite uniformly the swelling occurs, and even though there are some locally there are some swelling is small, but there are still sodium is there, so there is no problem for the heat transfer from pure slug to cladding. So sodium is a very good medium to accommodate any any discontinuity between pure slug and cladding. But after about some burnup, like 3% or 4%, normally the pure slug swell and it fully contact with the cladding.
Thank you. Why is the criteria of CDF so small, approximately 0.05?
It's good questions. This CDF is the subtle concept of the design parameter. It's only used on this SFR pure. It's not used in the light water reactor pures. In light water reactor, it always the outside pressure about 150 bar is higher than the inside the pure. But in this SFR, outside pressure is atmosphere, like 1 bar, but inside is high temperature. And that because of that, there are some during the irradiation, there are always tensile stress from inside to outside, and this stress change with the time depending on the temperature and the power and inside pressure. To consider those time changing the tensile stress, the concept of CDF is coming, and in locally the cladding, there are some non-uniformity of the cladding, like local thinning or others, and other barriers. And considering those local variations, I think that that's why the not the 1.1 theoretically 1.0 is the should be limit, but to be conservative, very conservative, it was set at 0.05 to consider all those uncertainties in the criteria.
Thank you. On slide 21, you identified a crack into the chromium coating. Was this the only one crack or for the whole rhodite, or were there multiple cracks seen?
Actually, for irradiation test, we didn't check all the pure rod. So there were, for Hanaro reactors, we found those cracks. Then after that, we worked hard to prevent those cracks occurring during the irradiations, and by forming some smaller multigrain in the chromium matrix. So unfortunately, we didn't do the second irradiations. So second irradiation will tell us how it behaves. Also, we did test in the APR in the Idaho National Lab with our chromium plated cladding tube, and if the PI is done, they will also show some how it behaves. Yeah.
Thank you. Has there been any consideration of also using a high entropy alloy mix for the fuel?
What that means? High end? What composition is mentioned about that? High entropy.
Dr. Hayes, will you give some more information on your question? It just reads, any consideration of also using a high entropy alloy fuel mix for the fuel? We'll see if Dr. Hayes will provide some clarification and follow up. In the meantime, Can your test results be used for US licensing? What are the QA protocols that you used?
QA protocols. We did for Hanaro irradiation test. We did our requirement for qualifications. So we have our qualification, and it's similar. I think it's quite strict, so it can be. I don't remember the ANS or I don't remember the exact name. The QA was applied for our Hanaro irradiation test.
Thank you. How much is the weight ratio of REMA in the fresh metal fuel?
What fuel, excuse me?
Fresh metal fuel.
Fresh metal fuels. For our Hanaro irradiation test, it's for our Hanaro irradiation test, we did make a pure slug with 5% of cerium content to check how it behaves. And we found because it's low temperature and low burnup, we couldn't find any significant difference compared to the uranium-10, just uranium-10 zirconium fuels. So we didn't find any migration of the cerium from pure slug to the cladding.
Thank you. Given all your challenges with casting and cladding, would you comment on using molten salt technology instead?
What is that mean, the molten salt reactors? I'm not sure. Where is the molten salt used? Is as a coolant instead of sodium, or just molten salt reactor, pure dissolved in the molten salt? Is that the questions?
I'm not sure. So, Mr. Steves, if you'll add some additional clarification to your question in the meantime. For someone not familiar with SFR fuel cladding concepts, can you discuss the relative merits of chromium electroplated cladded fuel versus sodium bonded fuel?
Yeah, okay. Even though with the chromium plated, there should be sodium bonded for this design. So this chromium barrier is good to prevent chemical interaction between pure slug and cladding. But even though with the chromium barrier, there need to be the sodium bonded for heat transfer. So chromium barrier is to help to prevent the chemical interaction to reach the higher burner. Also, for TLE fuel, if there are some high content of the chemically active layers, the barrier can help to prevent any adverse effect coming from the layers. So that is the reason we are working on the barrier development.
Thank you. Dr. Lee, on slides 25 and 26, you mentioned hydraulic and mechanical testing facilities. Are these designed to test spent fuel or just fresh fuel?
Just fresh fuel. We cannot do spent fuel. It's radioactive, so it's fresh fuel, and for licensing purpose, only the test of the fresh fuel is necessary. So we don't need to test with spent fuels.
Thank you. Do you use quartz glass for injection casting? If so, how do you treat the used quartz glass waste?
That's a good question. So we didn't actually work more about this waste of quartz glass. There are some studies in the, I think in the Idaho National Laboratory. It can be reused, or it can be used our other waste treatment purpose. So for that purpose, we didn't do much work on this quartz waste.
Thank you. Are fuel irradiation still being conducted in the bore 60? When will they be completed, or when were they completed?
When? So by it's reached about burn up 7%, and as I said in the final slide, we are waiting our government decision this year. So we hope the government allow us to continue the further irradiation in the BR60s. So we are waiting the government decisions about this one.
Thank you. We have some follow-up on those previous questions, which were confusing to us. Is it the intention? It is the intentional mix of 5 or more metals with some in low proportion to force chaos and arrangement, causing changes to crystalline and grain formation.
Excuse me, please explain again.
Sorry about that. It is the intentional mix of 5 or more metals with some in low proportion to force chaos in the arrangement, causing changes to crystallinity and grain formation, etc.
I'm sorry, it's about the question on the pure composition, or?
Yeah, the previous question, let me see if I can, I don't think it was the swelling. I think it was, it may be best if, Dr. Hayes, if you'll email, we can take it offline. That might be our best solution to this topic.
Yes.
Dr. Lee's email is on that Meet the Presenter slide, or if you send it to me, I'll be sure that he gets it, and we'll get you the question, the answer to the question that you're trying to ask. Do you have a plan? Yeah, do you have a plan for an irradiation of an annular fuel slug?
But yeah, we are working on, as I said, we are now at the stage of the annual production of copper. So if we have some, I should say it's long term, because we have some fund. I would like to have make annual fuel and to irradiate in our HANA reactors. For our, as I said, in second irradiation, we are still waiting. then about insert the campaign, we can do this annular and also the particulate pures. We hope to make the pure and irradiate in the Hanaro in insert the campaigns. Yeah.
Thank you. Dr. Lee, what advantages do you foresee using metal fuel over a MOX fuel in a fast reactor, considering the extensive experience in fast reactors for MOX fuel compared with the limited experience of metal fuels in fast reactors? Is the pursuit of metal fuel primarily tied to the use of the pyro process?
As I said, the metal pure has a higher thermal conductivity than oxide pures. So I think the regardless of the pyro processing, metal pure itself has a very good irradiation behavior in SFR. So I think the metal pure is better for the reactor safety than the oxide pures. Oxide pure have some potential to react with sodium, and there may be some concern about the failed pure swelling, which may result in the reduction of the flow, and it can. So for reactor safety point of view, I think the metal pure is much better than the oxide pure. That's why the even though 1-through cycle SFR fast reactor, the metal pure is the candidate, and those reactor development was done in the United States. In several, I think there are several designs just for metal pures in SFR 1-through. So yeah, that's my opinion.
Thank you.
Yeah.
And RE is difficult to remove from MA by the pyro process. How much do you expect the RE-MA ratio in the actual fresh fuel?
So this one depends on the purely on the pyro processing itself. So I'm not much familiar with the pyro processing, but they said to us it depends on the economy. By during the many step of the chemical processing, the content of layers can be decreased, but it is also related about the cost of the processing. So we are in conversation with their processing, how much can be allowed in the fuels. For example, the 5% of layers, it can be allowed in the pure fabrication and irradiation irradiation performance, or it can be lower than 5, or for example 3% of layers can be acceptable. So we are all in discussion with the pyro processing people. So I think it's optimization, kind of optimization, considering the economy.
Thank you. Dr. Hayes, I appreciate your effort to keep asking your question. It's because your facilitator doesn't have enough technology to formulate other than read the question on the screen. So with that caveat, the question reads, I have not always been the best communicator. A high entropy alloy is one where you take an alloy and intentionally put in other metals at low proportion to change the properties in many ways, which can increase strength and tolerance. The impurity metals increase chaos in arrangements and are called high entropy alloys.
Yeah, I not much familiar with high entropy, but I will answer. If you send me the email, I can answer. But in the inside the pure, there as a volume increase, there are lots of fission product accumulated in the pures. So in this pure slug, there are lots of the different fission products are mixed together in the pure slug. And those are the interact together, or some are migrating inside or outside. So in the pure slug itself, inside, during the irradiations, there are many elements working together to react. So I'm not sure how your idea of the mixing of different alloy elements will affect pure behavior. So it needs to be considered there are accumulation of the many different elements of the fission product inside the pure slug. Yeah,
Thank you. We have some great feedback, Dr. Lee. Thank you for a great presentation. Korea has an impressive and comprehensive program to develop and assess metal fuel designs. We look forward to seeing your further results. What welding process was used on the cladding and end caps?
Welding?
Welding. What welding process was used on the cladding?
It's TIG welding. We use the TIG welding.
Thank you. In general, is transmutation in a fast reactor more efficient and effective using metal or oxide fuel?
I think the metal fuel, as I said before, metal fuel can accumulate many different elements, and the microstructure is more, the alloy is more accommodated, can more easily accommodate different alloys. So for oxide, there are some, I think, the limitation for the sintering. If you insert many different elements, it may make more difficult to make sintering initially. So in that sense, the metal pure can accommodate more minor actinide, and that means the transmutation of the minor actinide can be more efficient in metal pures than oxide. And also the the energy spectrum of the metal pure design is more hardened. That means the high energy neutron is more available, so it's also more efficient to transmute actinide in metal case compared with oxide pure. Those are what I studied from the reactor design papers. Yeah, thank you.
Thank you. And I think we have time for maybe just one last question. Do you have any information about the situation of the Pride facility now?
Excuse me, again, please say the status of what?
It says the situation of Pride facility.
Clad?
PRIDE.
Pride. Pride. Pride is the pyroprocessing research facilities, and it's next to our building, and is ready. So same is our case. We are waiting the government decision this year, and we hope we have some positive signal and to continue to work on the this pyro processing, also to our pure research. So it's same as us. It's going there. It's still there, and we hope it continues. Yeah.
Thank you, Dr. Lee, for sharing your time and your expertise with us. It was a great presentation, and we can always get an indication of the engagement by the number of questions. And I think we had 35 minutes of questions, which is so fantastic. Thank you to the audience for being so engaged and bringing your enthusiasm to the topic. With that, I think we will conclude today's presentation. Patricia, did you have any last thoughts?
No, but like I said, you know, these webinars are very different because we have all these Q&A session at the end, very technical and extremely interesting question and answer. Again, thank you so much, Dr. Lee, for all the knowledge you have and you were willing to share with us. Thank you so much.
Thank you.
Thank you very much, Dr. Patricia and Bersa. Bye.
Thank you, Dr. Lee. Have a good day, everyone. Bye-bye.
Bye-bye.
Have a good day. Bye.